Hello, this is the rise of nanoparticles or nanoparticles. Nanoparticles, also known as nanomaterials, are categorized by a change in behavior when the substance is encountered on the nanoscale. Nanoparticles can be from any range of 1 to 1,000 nanometers. Nanoparticles can originate from either natural processes, industrial byproducts, or can be specifically engineered for their nano-sized properties. So fires is an example of natural processes, and diesel exhaust is an example of industrial byproducts. There has been an extreme increase in nanoproducts being sold, such as medical devices, pharmaceuticals, and cosmetics. Concerns regarding nanoparticles. So, an increased amount of nanomanufacturing and research are accelerating, leading to an increased number of nanomaterials entering waste streams and therefore entering the environment. Another concern is that few studies have examined the impact of nanoparticles on reproductive fitness. Also, little is known about how to clean up nanomaterial spills. So all these factors are kind of in the unknown on how it's going to affect the environment, reproductive fitness, and also just how to clean it up because there is very little research on how these nanomaterials or nanoparticles are affecting our ecosystems. Nanomaterials are not that different from other toxic chemicals used in industrial procedures and could have similar effects on health. But there's no way in determining this because there hasn't been, as I said, that much research done on how nanomaterials or nanoparticles affect a person's health or organism's health. Studies of chronic long-term nanoparticle exposure are needed, but hard to acquire test subjects since there is no person who has been exposed to nanoparticles who has completed their lifespan. This is more centered around humans because there hasn't been a human who has been exposed to nanoparticles for a long period of time or from the beginning of their life who has fully completed their lifespan. So there is essentially very hard to find an area of focus or examine how these nanoparticles affect a human's body, a human's functions, and etc. Another concern, and the most important, I believe, concern is that the everyday person is being exposed to nanoparticles that are found within everyday products such as makeup and sunblock. Since there is this increase of an everyday person being exposed to nanoparticles, um, that would raise a huge concern since we don't know the full extent or full effect of nanoparticles on the human. Main research question that is being asked from the article Rapid Evolution of Silver Nanoparticle Resistant in Escherichia coli is, can bacterium Escherichia coli K-12MG155 evolve resistance to citrate-coated silver nanoparticles AGMPS, and what mutations does that resistance arise? So the reason that they may be asking this specific research question is that engineered nanoparticles, ENPS, such as silver nanoparticles, are more prevalent in everyday products such as paints, sunscreens, and cosmetics. Since metallic/metallic oxide nanoparticles impact bacterial physiology, it would be difficult for bacteria to evolve resistance. If the bacteria can evolve resistance, then the use of nanoparticles can carry a risk of resistance development.
Figures 3A and 3B from the Graves et al. 2015 show the main results of this study. These are the two figures that support the idea that E. coli can rapidly evolve resistance to silver nanoparticles. The red circles represent the control bacteria that were not exposed to the silver nanoparticles, and the blue squares represent the populations that had been grown in silver nanoparticles for many generations. The x-axis represents the time of growth over a 24-hour period, and the y-axis is the optical density, which measures the bacterial growth. So the zero silver concentration grew normally, as shown in figure 3a, with exponential growth at 3 hours. The treatment groups with the 250 micrograms per liter had an exponential growth at 6 hours, but the control group with the zero concentration had reached an optical density, its peak optical density at 12 hours and then started dying, while the treated 250 microgram per liter continued to grow and reaching a higher growth rate still at hour 24. In figure 3b, showing the concentrations of 500 micrograms and 750 micrograms per liter, the controls were not expressed and were not able to grow, but the evolved populations, still the blue squares, were able to grow. The 500 microgram per liter grew exponentially at hour 6, while the 750 grew exponentially at hour 12, showing how strongly the E. coli was being able to adapt to the silver, building up its resistance. So overall, the control populations die when exposed to the silver nanoparticles, while the evolved thrive. This supports the idea that bacteria can evolve to be resistant to silver nanoparticles pretty quickly.
Arthur's main conclusions. In their study, Graves and colleagues challenged the long-held assumption that metallic nanoparticles are evolution-proof. They demonstrated that E. coli can rapidly develop resistance to silver nanoparticles in approximately 225 generations, less than 2 months in bacterial time. The researchers identified specific gene mutations that enabled bacterial survival, showing that resistance arose through adaptive evolution rather than random chance. This finding is significant because silver nanoparticles are widely used in everyday products such as bandages, cosmetics, and disinfectants. The authors concluded that improper or excessive use of nanoparticles can contribute to the emergence of new forms of microbial resistance, paralleling antibiotic resistance, with major implications for both public health and environmental safety. Key new learnings and what we found fascinating. As a group, we were really surprised to see how quickly bacteria can adapt to something as modern as nanoparticles. We had assumed that silver nanoparticles were a long-term solution for killing bacteria, but this study showed that they can actually promote resistance instead. We also thought it was fascinating that the mutations occurred in existing genes like the CUSS and RPOB, which bacteria already use to sense and respond to metals. It showed us that evolution doesn't always create something new, it can modify what's already there to solve new problems. Finally, we learned about experimental evolution. It was really eye-opening for us. Being able to observe adaptation happening in real time helped us understand how evolution works as a continuous, measurable process rather than just a historical one. Overlapping evolutionary concepts. Overall, this research helped us see the connection between nanoscience, evolution, and microbiology in a much clearer way. It ties directly to class concepts like natural selection and adaptation. In the experiment, some bacteria carried mutations that made them slightly more resistant to silver. After repeated exposure, those bacteria survived and passed on their traits, a direct example of Darwinian selection in action. We also realized that human technology itself can become an evolutionary force, just like antibiotics. Nanoparticles can shape how microbial populations evolve over time. Seeing these processes occur in a laboratory setting made evolution feel much more tangible, not just a theory in textbooks, but something we can actually observe happening within just a few weeks.
Here are the references.
Thank you all for listening to our presentation.